All right, guys, and we're back moving on into the second part of our notes right here from section 4.2. So what we had just finished, and I lost the file with all my notes in it, oops, is that we had been talking about these 6 graphs right here and trying to describe where we had extreme values, whether they were absolute maxima, absolute minima, relative max, or relative min. And we did a bunch of graphs like that. And now we're going to move on into this. Okay, this is an important vocabulary word here, everybody. Important for what it is that we're talking about right now, but to be honest with you guys, year in and year out, this is one of those phrases that shouldn't be that tough to get down, but people miss points later on in the year as we're getting ready for the AP test, simply because they forget the definition of this important term here. So a critical point, everybody, we're going to define right here in the following way. That the ordered pair a comma f of a is a critical point of your function f of x if one of the two following things happens. If f prime of a, the derivative of your function, evaluated at this value here, if f prime of a is equal to 0, or, and or is important now, either one of these can do it, if the derivative at that point does not exist. If either of those two things happens, then we have a critical point at that particular point in question. So I just drew 3 real quick graphs right here that we were going to discuss right here, and we'll see what's going on in each one of them. Now, what you're going to start to sense here pretty quickly is that when we have a critical point, certain interesting things kind of happen on the graph, all right? So, y equals x squared. Real quickly, guys, I'm going to do some informal notation right here. Y prime, then, our derivative of x squared would just be 2x. All right, and is there any value of x that would make this derivative either equal to 0 or undefined? All right, well, pretty clearly, that one is going to equal 0 when x is 0. So at this spot right over here, everybody, we have ourselves a critical point because our derivative is 0 at that spot. And of course, that shows up, everybody, as a horizontal tangent since the derivative tells us the slope of our tangent. The other thing we should think about, the second part of that definition, which you can still see right here, you also have a critical point anywhere your derivative does not exist. So you should ask yourself, is there any value of x that we could put in there and not get a real result? The answer to that is no. Our derivative here is a simple linear function, 2x, and a linear function, being a subgroup of polynomial functions, is defined for all real numbers. So we only have the one critical point here on the graph of y equals x squared, and that is at, you'll notice, the vertex of the parabola. Let's take a look at b. In this case right here, guys, y prime, our derivative, is going to be 3x squared. And once again, you want to consider 2 things. First of all, is there any value of x that's going to make that derivative equal 0? And the answer to that is yes. That again happens when x is equal to 0. So we have another critical point right here. And even though my graph isn't very good, guys, that almost looks like more of a tangent graph, we do have a horizontal tangent here passing through the origin on this. And the second end of that question, is there any value of x for which 3x squared is going to be undefined? The answer to that, just like it was in part A, is again going to be no. Your derivative is a polynomial. Polynomials are always defined. So we have one critical point right here at the origin in this graph. Now I wanted to talk about these two problems side by side though, dang gummit, side by side to make an important distinction. In example A, our critical point happened to be an extreme value. That critical point right here, everybody, is the absolute minimum of that function. But in B, our critical point right here at the origin is neither a maximum nor a minimum. It goes down as the function moves left, and it goes up as the function moves right. So what those two examples side by side should show you is that a critical point can give you an extreme value or can occur at an extreme value, but it doesn't have to. And we'll talk more about that in just a second. Now, the last example that I wanted to do with you guys was C, which is y equals the absolute value of x. And I didn't write that out, although I certainly could. Y is equal to the absolute value of x. And the reason I didn't really bother to do that is because the absolute value of x is an unnatural function. It's not one that we can differentiate here by normal methods. So what's really going on here, guys, is that your derivative, y prime, is piecewise defined. That derivative is always going to be a negative one when x is less than, whatever the x coordinate of your vertex is, which we're going to generically call h. So anywhere x is less than h, the slope of your tangent is going to be negative 1, and it's going to be a positive 1 anytime x is greater than h. Now you'll notice, everybody, on purpose, I didn't put an or equals to here, nor did I put an or equals to there. And the reason for that is, if we go way back to the beginning of chapter 3 when we discussed the concept of differentiability, this function doesn't have a derivative at x equals h, at its vertex. This is a spot right here, guys, where the left and right-hand derivatives are not the same. The left-hand derivative is negative 1, the right-hand derivative is positive 1. And so for that reason, everybody, we do have a critical point right there at x equals h, because this is a spot not where the derivative equals 0. This is a spot, let's go back to the second part of this definition, this is a spot now where the derivative does not exist at that point. So unlike a and b, this is important, guys, please pay attention to this. Unlike a and b, this graph in C does not have a horizontal tangent at its critical point. The horizontal tangent exists because the derivative exists and is equal to 0. But right here, guys, in the graph of C, this one does not have a derivative at x equals h, and so there is no tangent line at that spot. All right, so before we move on, I want to make sure one more time that you guys have this information written very, very clearly in your notes, that a critical point can occur anywhere that either the derivative equals 0 or where the derivative is undefined. So put a big star by that, because again, this is a definition that's going to keep coming back all year, and people tend to goof it up year in and year out. Now that being said, this is another one right here that you want to make sure that you get very clearly written in your notes. Because again, it's a relatively simple concept, at least to understand it at this base level, but people tend to get this wrong. Extreme values of a function can occur only at two things, guys. They can occur only at critical points and only at endpoints. Although to be clear, we're only going to have endpoints when we're dealing with a closed interval. So what do I mean by that? If we were going to talk about where are the extreme values of a function, and I drew a curve that looked maybe something like this, the fact that I've put arrows on both ends of that figure means that this function does not exist on a closed interval, but rather on an open interval. So the only possible extreme values would occur at critical points. There'd be one right here where the tangent line would be horizontal, meaning that your derivative would equal 0. And there's another one right over here where the exact same thing happens. Ooh, that's a good tangent I just drew. I'm impressed. All right, that your derivative would equal 0 and you would have a horizontal tangent there. The way I've drawn this right now, those are the only possible extreme values. And it looks like this first one that I drew is a relative maximum, and it looks like the second one that I drew is a relative minimum. But if I wanted to get a little bit more creative with this graph, I could get rid of some of this stuff, and I could put a closed dot right here and a closed dot right here. And now for the first time, we are dealing with a closed interval. And that means that this point here, the left end point, and this point here, the right end point, those can now be extreme values. And back to what we were doing in the previous video, you guys, now I think what's going on is that this point right here now looks like it's an absolute max, the highest one. This one way over here on the left looks like it's our absolute minimum. This third critical point that I have looks like that one is going to be a relative minimum, and the right endpoint now looks like it's going to be a relative maximum. But the important thing is here, everybody, to take away from this slide, the only possible places you can have extreme values are critical points and endpoints. This point right here, this green dot, is not a critical point. Okay, our derivative is not equal to 0 and it's not undefined there, nor is it an endpoint. So this is just a random point. It can't possibly be a max or a min. Anytime you have a max or a min, it has to occur either at a critical point where the derivative is 0 or undefined, or at an endpoint. So again, not a super difficult concept right here, but people tend to make mistakes on quizzes and tests, I'm sorry to say, because they don't know this basic fact. So those last two slides, all right, the one right here where we talk about the definition of a critical point, and then this second one here where we talk about where extreme values can occur, those are two really important, simple, but important ideas to get down. All right, so let's talk about this one right here, number 5. And this is an important example to work through as well, everybody. This is one you're going to see a lot of questions similar to this on quizzes, on tests, and this type of problem shows up on the AP test as well. So we really need to know how to do this. We're going to find and classify all extreme values of this polynomial function. We have a cubic on a closed interval from 0 to 6. So again, we're looking for extreme values. So I go back to the previous slide and I say, aha, extreme values can only occur at critical points and endpoints. Well, pretty obviously, we've got two endpoints right here, 0 and 6. So let me put a star by those. I got to figure out what's going on at the endpoints. The other question, though, is where are their critical points? So now I go back 2 slides. And I say, aha, again, a critical point is a spot where the derivative equals 0 or where the derivative does not exist. So we're going to have to find our derivative. And again, guys, this gets into the main idea that we're doing here in Chapter 4, applications of the derivative. We can use our derivative now to find out important information about a function, including its extreme values. So f prime of x looks like it's going to equal a 6x squared, a minus 30x, and a plus 24. 2 questions. Is that derivative ever going to equal 0? I think the answer to that is yes, but we'll find out. And the second question, is that derivative ever going to be undefined? The answer to that is no. This is a polynomial derivative. Polynomials are always defined. So let's see what we can't do about to solve this. Now, if you were allowed to use your calculator, you could just type it in and say solve that equation, but what fun would that be? I'm going to factor out the 6, and that'll leave us with an x squared, a minus 5x, a plus 4, all is equal to 0, and now that looks like a quadratic trinomial that is going to factor. I think we're going to have an x minus 1 and an x minus 4. Let's see, yeah, that works. And now we solve each one of these, or I should say we set each one of those factors equal to 0 and solve. Well, there is no solution from 6 equals 0. Can't happen. But x minus 1 equals 0, yeah, that gives us a solution at x equals 1. And x minus 4 would equal 0 when x was equal to 4. So right now, guys, we've just come up with 2 critical points, 2 values of x for which x is, the derivative f prime of x is equal to 0. Now I want to be clear. Those are critical points, definitely, because those are values of x that make f prime, the derivative, equal 0, but they're not necessarily extreme values, and we don't know that yet until we do a little bit of testing. So what's important to understand right now is that we have identified 4 potential points for extreme values. The 2 endpoints right up here at 0 and 6, and then the 2 critical points right here at 1 and 4. And we're going to need to figure out what the y value of this function is at all 4 of those points before we know for sure what's going on. So I'm going to write them in order, everybody. 0, 1, 4, and 6. So I'm going to go to a new page here because I'm running out of room, and we're going to go ahead and we're going to evaluate the function at each of those 4 values. F of 0, f of 1, we have an, we have an f of 4, and we have an f of 6. All right, how easy is this going to be to do in my head? Well, f of 0, yeah, I can handle that one. 0 minus 0 plus 7 is going to give us 7. So we know that this graph begins at the ordered pair 0, 7, but I have no way of knowing, everybody, whether that 7 is a high point, a low point, or anywhere in between until I actually look at it relative to everything else that's going on around it. So that's not a whole lot of help right now. Let's go ahead and let's evaluate f of 1. So looking back at the original function right here, putting in a 1, we're going to get a 2 minus 15, that's a negative 13, plus 24 is going to get us 11, and 11 plus 7 looks like it's going to be 18. Let's try that again. What in the world? No, I don't want that. 18. There we go for that y value right there. The one thing I know, everybody, 7 is not the absolute maximum of this function. How do I know that? Because there is a y value, 18, that's higher than 7. And likewise, I know that 18 is not my absolute minimum. But let's move on from there. Plugging in a 4, obviously you guys would want to use a calculator here, but let's see what we can do. 2 times 4 cubed, that's going to be a 128. I'm going to write that over here. Minus 15 times 16 is going to be a 240. Gotcha. Plus 24 times 4, that's going to be a plus 96. And a plus 7. So I don't know. Let's see, guys. We're at a negative 112. Add 96 to that. We're at 16. 16 plus 7, I think, is 23. But I'd feel stupid if I got that wrong. So I am going to cheat now and grab my calculator, assuming my initial calculations were right. Plus 96 plus 7. Oh, that didn't seem right. Nope, I think I goofed that up. That was a negative right there, 16, not a positive 16, dummy. Yep, okay, my mistake. That's why you check. That should have been a negative 9 there, everybody. All right, so assuming that's right, f of 4 is now negative 9. Okay, and now let's try it with plugging a 6 in there. So I'll just go ahead and do this one all the way out. Here we go. So we've got 2 times 6 to the 3rd power. All right, minus a 15 times 6 squared I can do in my head, that's a 36, plus 24 times 6, and then a plus 7. I came up with a 43 then for the value of f of 6. Okay, so now that we have figured out all of the y values that occur at the only 4 points where extreme values could potentially occur, we're now ready to make our distinction. Notice the problem here said find and classify all extreme values. So I'm going to start, as I always do, with the absolute maximum. The biggest y value we are ever going to get here is 43. So that value there is your absolute max. And remember, guys, when they ask for an extreme value, they're just asking for the y value. So the answer to that question is my absolute maximum is 43. My absolute minimum is the lowest y value we came up with. That's the negative 9. So that is going to be our absolute minimum. Got that. Okay. And then from there, let's think about what's going on right here. We started at the ordered pair 0, 7. And then as we move from left to right, we went up to get to the ordered pair 1, 18. So 0, 7 was actually a low spot that we then moved up from. So this one right here, that 7, is going to be a relative minimum, lower than all the points immediately around it. And the 18 then, everybody, is going to be a relative maximum. Okay, so there we've gone ahead and we have found and we have classified all of our extreme values within this particular function. Now, just to illustrate what's going on right here, let's take just a second. I'm going to go to my CAS app here. We're going to go ahead and graph this one just to verify that what we did here was correct. So let me go here. It looks like I have something going already, but I don't think I want that anymore. So, okay. Trying to remember how to do this, guys. You tap somewhere here. There it is. All right, I'm going to hit my up arrow, and I'm going to get rid of that junk for F1. And the function we were dealing with right here was a 2x to the 3rd power. Okay, gotcha. 2x to the 3rd followed by, I lost it here, minus 15x squared plus 24x plus 7. So a minus 15x squared. Gotcha. I believe it was a plus 24x and a plus 7. I think I should probably verify that, though. Plus 24x plus 7. Yeah, I think we got it. Okay, so with all that in mind, there's our function. And if I go ahead and hit enter, whew, I get this interesting thing. Now, this is more of the graph than what I actually want to see. And on the iPad, it's pretty easy. I can kind of pinch and zoom and do some things like this. What I think we really want to do, though, and you guys can do this on your calculator as well, I'm going to change my viewing window so I'm only looking at the stuff that's necessary. So I go to Window, Zoom, and I'm going to go to Settings now. Now, the minimum x value that we cared about on this interval was 0. So I'm just going to type that in. There's really no point in looking at anything more than that. Okay, the maximum x value that we cared about, how do I get to, there's a tab button here somewhere on your calculator. All right, I guess I got to do this the hard way. The maximum x value that we cared about was 6. Cool. As far as the y minimum, I believe, now I could be wrong about this, but we'll find out if we are or not, I believe that the minimum y value that we came across right here, that would be our absolute minimum, would be -9. So just to give myself a little bit of breathing room, I'm going to put like a -10 in there, all right? And the maximum y value that we came up with was, forgot that too, absolute maximum looks like it's going to be 43. Okay, so again, I'm going to give myself a little breathing room and I'm going to put a 45 in there. Okay, cool. And let's hit OK. And let's see what this graph looks like here, everybody. This is the only part of the graph we care about. We're not really concerned about what happened to the left of x equals 0 or to the right of x equals 6. And it certainly does look, everybody, that we started, boy, I wish I could draw on this and I really can't, I'm sorry, but we started in this lower left-hand corner over here with what looks like a relative minimum. Then as we progress, I guess I could trace this maybe? So you guys could see what I'm talking about right here. No, I don't want zoom. Let me go trace and graph trace. Okay, and what did I learn the other day? If you double tap, you can put in a, I thought, double tap the point. There you go. And when I put in a 0, okay, so down in the lower right-hand corner of my screen, everybody, you can see the 0, 7. So that does look like a relative minimum. Now as I drag that a little bit further to the right, I should be coming up on a maximum right there. And if you guys will notice, this is a nice feature of the Inspire CAS, and yours will do that too. It'll tell you when you get a maximum at the point 118. It doesn't tell you if it's a relative or an absolute, but we were able to figure that out. So there was the ordered pair 118. That's at a relative maximum. Next thing, at the point 4, -9, we think we have an absolute minimum. So let's see, we drag this along, and at some point it's going to tell me, I think, there it was, that we had a minimum, yep, at 4, -9. And then on that interval, it probably won't tell me this right here, but it looks like we hit a max value right here at x is equal to 6 and a y value of 43. Okay, so that graph certainly seems to support what we came up with here in our work. I guess I could be a little bit more complete here and say, okay, the graph did this, and then it went lower, and then it went higher. So here was the relative min, here was the relative max. Sorry, ran out of room, but the absolute minimum would be down there somewhere, and the absolute maximum would be here. All right, so guys, that is an important example for you guys to have in your notes and for you guys to understand how we do a problem like that. First, we found critical points by setting the derivative equal to 0. Then we took both our critical points and our endpoints, and we had to test the value of the function at those x values, at the potential locations of extreme values. 1, 4, 0, 1, 4, and 6. And then only by looking at the 4 y values were we able to determine which were absolute max, which were absolute min, relative max, and relative min. All right, we're getting close to the end of this here, guys. The last thing that your author threw in this section, in hindsight, I wonder if maybe I could have done this a little bit earlier, but it's not real important. Seems a little odd to throw a theorem at you at the very end of this section, but it's a pretty quick and not terribly consequential theorem. If f of x is continuous on a closed interval from a to b, then f of x has both an absolute maximum and an absolute minimum somewhere on that interval from A to B. Guys, I'm going to draw 3 quick, simple graphs to try to illustrate what's going on. But I think that each of these is going to harken back to something that we did earlier in this section. So what do I want to draw? A function that's continuous on a closed interval here. So I'm going to draw something that is weird and kind of ugly, but it is a function and it is continuous on this interval here from a to b. And the extreme value theorem tells us that if your function is both continuous and it is a function on that interval, then you're guaranteed the existence of an absolute max and an absolute min. And sure enough right here, guys, we have an absolute maximum right here, and it looks like we have an absolute minimum right there. Okay, that's what the extreme value theorem says. So this is kind of the positive example, everybody, so you might want to circle that. Now, there are, what do I want to call them, anti-examples as well. Let's go back to a problem that we talked about earlier, which was this one right here. You'll remember this from earlier in the notes here, all right? And the function looked like this. Now this function is continuous on a closed interval that starts at a, and it is continuous at a, but it is not continuous at its right endpoint because we have that open dot up there that was at b comma 5 or whatever it was before. And so what I need everybody to understand is that this function here does not satisfy the hypothesis of the extreme value theorem. This function is not continuous on a closed interval from a to b, and therefore it's not a guarantee that what comes after it doesn't work, but it means that everything that comes after that is invalid. There's no point in reading the conclusion of a theorem and trying to apply it to a graph here if this graph does not satisfy the hypothesis of the conclusion. Maybe this graph has an absolute max and maybe it has an absolute min. Maybe it doesn't have either, and maybe it only has one. And if you remember, this graph right here only had one. So, because this second graph does not satisfy the hypothesis of the theorem, don't even bother trying to make a conclusion out of it based on what it says. All right, I didn't want to cross out my beautiful theorem right here, but okay. However, I do want to make one more point. I'm going to go ahead and show you a graph that looks like this. I'm going to start it at an open dot. I'm going to have it go up and then come down and then come back over here, and I want to end it at an open dot. That was actually supposed to connect there. Wow, nice graph, Mr. Fontana. Okay, let's read the theorem. If your function is continuous on a closed interval from a to b, this one is not. This one is not continuous at a, nor is it continuous at b. So just like the second example, this one right here does not satisfy the hypothesis of the extreme value theorem. Therefore, once again, you should ignore the conclusion because it's inconclusive. But you guys need to be careful not to make this false reasoning jump right here. It's tempting to say that, okay, if the theorem is right, as was illustrated right here, if it is continuous on the interval from a to b, then it has both an absolute max and an absolute min. It's very tempting then to say that the inverse would be true. If the function is not continuous on the interval from a to b, then f of x does not have an absolute min and an absolute max somewhere on the interval from a to b. And everybody, that statement is false. The reason that I wanted to draw this is because this is an example of a function that isn't continuous, and yet it does have an absolute max right here, and it does have an absolute min right here. So let me get rid of some of the junk here and try to clean this up just a little bit. What you guys should take, these two right here are anti-examples, all right? These ones don't illustrate what's happening in the extreme value theorem, but what I wanted you to see by looking at the second and the third graph side by side is that if the hypothesis of the theorem is not satisfied, you can't make a conclusion as to whether or not it does or does not have an absolute max or an absolute min. It might not. It might have both, it might have none, and it might only have one. So don't get in the habit of saying, okay, if A, then B, all right, that does not mean that if not A, then not B. Okay? That's a little bit of a logical step right there, and if anybody's going to be a philosophy major in college, you'll get a little bit more practice at stuff like that. All right, guys, that's a wrap, I think, on our notes for 4.2, so let's give that a shot. Do the best you can on the homework, and let me know when you guys have questions. Good luck.